Hello and welcome to Lecture 15, where we're going to cover more on geometric optics, also known as ray optics, and cover the second half of Chapter 22 and the beginning half of Chapter 23 from Survey 11th edition. Okay. In the first half here, we're going to cover the topics of dispersion and total internal reflection, with objectives to understand that dispersion is caused by different wavelengths of light having different indices of refraction in certain materials, and understanding that total internal reflection occurs when a refracted angle is greater than 90 degrees, and that is measured relative to the normal. All right, so for dispersion, this is the idea that for some materials, the index of refraction is dependent on the wavelength color of the light. Okay. And for critical angle, the critical angle is the angle of incidence that creates total internal reflection. So this is a angle theta 2 that is greater than or equal to 90 degrees. All right, so this would be the actual refracted angle. Okay, and the critical angle is the angle that makes that possible. And this requires that N1 is greater than N2, or to use the subscripts in the figure below, it'd be NB, or in the equation below, NB and NA. So let's take a look at that equation. So this formula here presents the critical angle, and so the idea is that sine of the critical angle is equal to NB over NA. NB would be the index of refraction of the material that the light is being transmitted into, and NA is the material in which the light is incident. So that's the light going from material A into material B. Okay, and we can see that this formula will only work. It will only produce a value as if. So in other words, there's only a solution if, when you do sine inverse of both sides, in order to isolate your critical angle, you see that NA must be greater than NB, because otherwise you would have a ratio here that's greater than 1, and you can't take a sine inverse of any value greater than 1. You'll get no answer, an undefined answer. And so indeed that's the case, is that the material that NA must have a higher index of refraction. So for example, total internal reflection is possible for light that is inside of glass and is traveling into air. So that's one way to create fiber optics, for example, is to have light inside of glass surrounded by air. And in that case, the light can stay trapped inside the glass with none of it being transmitted out into the air. So let's look at an example that meets that criteria of having NA greater than NB, and that is an underwater lamp submerged in a lagoon at night that emits light in all directions at a depth of 7.2 meters. And so an observer in a boat would see a circular region of light and that has a diameter of what? Okay, so the picture would look something like this. Here, actually I already have it started. So here we have a picture showing the water, and we have our lamp at a depth of 7.2 meters. We're interested in finding this critical angle. So that's the maximum angle that the light would travel, because for any light ray that is coming to the surface that is going to be making an angle larger than the critical angle, all that light would get reflected back down in the water. At exactly the critical angle, the light would come up, look like this, and then it would get transmitted exactly at 90 degrees. For a steeper angle, like the one shown here, the light comes up and then comes back down into the water, because that's an angle greater than the critical angle, and so then the light is being reflected completely. So then the illuminated region that someone above the water would see would just be a circle of light with a diameter that we're going to solve for. So we'd start by finding that critical angle, and when we take sine inverse of 1 over 1.5, we get 41.8 degrees. And so then if we think about our triangle, we know that this angle here is equal to that. Those are equal angles. And so then we know that tangent of the critical angle is then there's going to be equal to R over D, or I should say D 1/2 of D and over the depth, which I can't call d because we've already called the diameter d, so we'll just take it over 7.2 meters. So that's just opposite over adjacent relative to this that angle shown there. And that's with this right triangle. And so when we do that, and then we solve for the diameter, and so then d is just going to be equal to 2, and then so it'll be 2 times 7.2 meters times tangent of 41.8 degrees, and that gives us 12.9 meters. Okay, so that would be the diameter of the light circle as seen from the surface or from someone in a boat. Okay, so that's example 1. Let's take a look at this question here. So based off the figure, which color of light is refracted more in the prism, red light or violet light? Well, looking here, we can see that, just looking at this first refraction going from air into glass, presumably what the prism is made out of, we see that we have that the red light got bent some, but the violet light got bent more. So the violet light is being refracted more. So the violet light is refracted more. And that's consistent with the figure from the previous page that showed that it is the blue, the violet light, the shorter wavelength lights that have colors of light that have a higher index of refraction for materials that have a variable index of refraction. And the longer wavelength light, the red light, orange light, in materials that those index of refraction for those colors is going to be lower. Okay, so they won't get bent as much because the lower the index of refraction, the less bending. Or the higher the index of refraction, the more bending. If we look at when the light comes out of the prism, shown here, we would expect that the red light is going to not bend as much back away from the normal, and indeed, that's what we're seeing. That the purple light bends more each time, so it bends towards the normal more when it passes into the prism, and it bends away from the normal more when it passes back into the air. All right, so let's actually look at a computational example that involves the dispersion of light. So the index of refraction for violet light in silica flint glass is 1.66, and that for red light is 1.62. Okay, so these would be like values that we saw in the figure on the previous page. What is the angular dispersion of visible light passing through a prism of apex angle of 60 degrees? Okay, so this angle here is measured to be 60 degrees. All right, and we've got, and the angle of incidence is 50 degrees. So then relative to the normal direction, we have that this angle here is 50 degrees. Let's get the normal shown. Okay, and so this angle is 50. Okay, so apex angle 60, incident angle 50. All right, so let's figure out what our dispersion looks like. Okay, so we just want to kind of set up a general form here. So I'm going to label some angles. So we have, for the first case, relative to the normal, we'd have what I'll call theta, we'll go ahead and call that theta 2. Okay, and then this angle here would be our theta 1, which is given as 50 degrees, our incident angle relative to the normal. And the theta 2 that I drew is kind of being shown for purple light. I guess I could draw it a bit better, maybe to show it for red light as our baseline. So let's go ahead and do that. So this will be, okay, I'll call that theta 2. So there we should have the light bending towards the normal. So we should certainly find that theta 2 is less than theta 1, because as the light goes from lower index of refraction here to a higher index of refraction there. It should bend towards the normal direction, try and take a straighter path through the prism. Then we need to draw two more angles on the way out of the light, or way out of the prism, the light on the way out. Okay, so we'll do that like so. Okay, and so here I'm going to have a theta 3 and theta 4. All right, so this angle right here, this one I will call theta 3. And then this one will be theta 4. Okay, so those are our four angles. This is much like the post quiz of light traveling through a prism, because you have refraction both on the way in and the way out. Okay, and so if we set up and think about Snell's law and the geometry involving the apex angle, we would get something like this. All right, so we'd have n1 sine theta 1 equals n2 sine theta 2. That's Snell's law passing into the prism. On the way out, we would have n2 sine theta 3 equals n1 sine theta 4. Lastly, we have that theta 3 is going to be 60 minus theta 2. Okay, so it's going to be, I should give this apex angle a name. I'll name it alpha, just like in the quiz. And so the idea then is that, so sort of our last governing equation here is that theta 3 is related to theta 2 and alpha by simply being alpha minus theta 2. All right, and you can think about the geometry, how those angles are related to each other. Okay, so you can get an idea about that. Okay, and so then we want to think about how we'd solve for theta 4. So we can kind of do this algebraically, and we say, okay, well then theta 4 is going to be n2 over n1 of sine of theta 3, all inside a inverse sine function. Okay, so that would look like so. So sine inverse, like that. Okay, then I'm going to replace theta 3 with alpha minus theta 2. So I'll rewrite that one more time. So sine inverse, and then n2 over n1, and then sine of alpha minus theta 2. Okay, well, really the next step is then to replace theta 2 with an expression that's dependent on theta 1, because then we can just plug in our different indices of refraction and just kind of have our ready-made formula. So the last step then is I'll write as theta 4 one more time. So theta 4 is then going to be sine inverse and n2 over n1 sine of alpha minus, and then here just using Snell's law again, which would be this top equation here. I'm just then going to write that theta 2 is sine inverse of, and then here I would have n1 over n2 times sine of theta 1. Okay, with theta 1 being given. So we'll close off all our parentheses. There we have it. Okay, so this formula looking large, but being very effective for plugging in our values, really is then able to solve for theta 4. And in doing so, we can just plug in our given angle, and then we can plug in our indice of refraction that's specific to the wavelength. In both cases, n1 is just going to be equal to 1 because it's air. So then we could say, zooming out a bit, that for red light, we'd have that theta 4 is just going to be equal to sine inverse, and then 1.62, and it'll be 1.62 divided by 1, but again, n1 is just equal to 1, and then 60 minus sine inverse of 1 over 1.62, and then times sine of 50 degrees. Okay. And that ends up being 58.6. Okay, so 58.6 degrees for red. For violet, we do the same thing, except here we're going to use the index of refraction specific to violet, so it'll be 1.66. But otherwise, the identical setup. Like so. Okay, and so for violet then, we get a final angle of 63.2 degrees. So that means that our difference, our spread, and so our dispersion angle is just going to be theta 4 violet minus theta 4 red, which is 4.61 degrees. Okay, so there we have how much dispersion there would be between either end of the rainbow. Right, so the maximum dispersion of visible light for this particular prism. All right, so you can really see how dispersion follows naturally out of Snell's law by just having a variable index of refraction. All right, so I have further examples that you can look at for practice. Okay, so we have another example of a critical angle. We have another example of a critical angle, this case for having a beam of light that is bounced around a pair of binoculars. And then and yet another critical angle example. So a lot of further practice if you want more practice. Okay, so let's move on to the second half of this lecture, but I will start that in the next